All right. Hello, modern algebra people. Okay, this is Paul Hazelton. The claim is, suppose G is an abelian group and let H be the set of, for all things x in G, such that the order of x is finite. Show that all non-identity elements in G mod H have infinite order. So for the proof, I'm just going to read this and then go through it a bit more. Let G be an abelian group, and H is that set with x in G such that the order of x is finite. Let AH be an element of G mod H such that AH does not equal H, that is, such that A is not an element of H, and AH is a non-identity element. This also implies that the order of A is infinite since A is not an H. Now this right here, the order of A is infinite, because we said A is not in H, and if it was in H, the order would be finite. But it's not in H, so it's the opposite, it's infinite. Assume that the order of AH is finite, and this is setting up a proof by contradiction, so we're assuming the opposite of the claim. Since the order of AH is finite, there exists an n in the integers such that AH to the power of n equals H. But AH to the power of n equals A to the power of n H, which equals H. So A to the power of n is an element of H. And since A to the n is in H, we know there exists some number k in integers such that that element to the k is an identity, is the identity, and A to the nk is the identity, which implies that the order of A equals nk and is finite. And lightning bolt! That is a contradiction because we said from our setup that the order of A is infinite since it's not an H, but we said down here that it's finite. So our assumption that AH is finite is bogus, and the order of AH has to be infinite. Proof done. Thank you very much.